Hello everyone, today we will talk about universal gates and we're going to talk about NAND gate. There is also another universal gate called NOR gate and we're going to talk about it next time. So this is very straightforward. I'm going to tell you about how NAND gate works, what it is, and how to use it. And you will see towards the end that we can build everything with a NAND gate, just one gate. We can build any AOI logic circuit, that's AND or inverter, with just NAND gates. So that's very useful because that's more standardization. So I think you will see that it usually comes out to less integrated chips too. So that costs less money, and what's more important for us in particular, we have to breadboard less. So this is what a NAND gate looks like. And you can see that it looks like an AND gate with a little circle. Now, circle generally means inverting the input. So if you look at this over here, this looks a lot like an AND gate. If I were to draw a truth table for the AND gate, here's my truth table. 0, 0, 0, right? 0, 0, 0, 0, 1, excuse me. 1, 0, 0, 1, 1, 1. You can see that this gate over here is actually an inverted version of the AND gate. And that is literally what NAND gate is. NAND is just not AND. If I wanted to build an NAND gate out of an AND gate and an inverter, it would look like this. I would have an AND gate. And then I would have an inverter straight after. So this is essentially what a NAND gate is. Now I told you that you can use NAND gate as any gate. So you can NAND gate as an inverter. You can use NAND gate as an inverter. All you have to do is tie these two inputs together, right? This way your entire AND gate will become an inverter. So let's see why this is the case, okay? So here's your truth table in this case, right? Well, the truth table for NAND gate was, remember, 0, 0 gives you 1, 0, 1 gives you 1, right? 1, 0 also gives you 1, and 0 and 1, 1 gives you 0. It's an inverted AND gate, right? So let's take a look what I have over here. So I have X coming in over here and X coming in over here. So if X is 0, then I have 0, 0 coming in and the output is 1. Okay, so that's that one. Now what if X is 1? Then I have 1, 1 coming out and that's a 0. And you can see that the resulting truth table is exactly the inverter. So this is very easy to turn a NAND gate into an inverter. I know it sounds a little convoluted that you're tying two inputs together, but you will see that it actually comes out to simplifying things in the end. Okay guys, so this one is very straightforward. How do you turn a NAND gate into an AND gate? Well, first we need to remember what I just told you, right? That a NAND gate is not an AND gate, right? It's an inverted AND gate. So this is what your NAND gate is in terms of the inverter. So all I have to do to turn it back into an AND gate is either take off the inverter or invert it back. I can add another one, right? Remember, inverter plus inverter is just regular signal, right? So this is literally what I have drawn over here. So this is my NAND gate, and this is my inverter. And this is my inverter. And guys, it seems like it's a little weird the way I'm doing this, because it seems like I'm adding more stuff that is not necessary. But you will see once we start re-implementing the circuits that it actually really does work beautifully. Now, next one is how to use a NAND gate as an OR gate. And this is finally, you get to see the reason why I taught you De Morgan's, okay? Because this is a straightforward application of De Morgan's. So I want to turn something that looks like an AND gate into an OR gate. Well, if you guys remember De Morgan's, then we had this kind of rule in there, right? That you can turn a multiplication into the addition, you break the line, you change the sign, right? So here you go, right? So this is your De Morgan's, right? So we're going to do that exact application, except in the end, we want to have our X and Y to not have that line on the top. So that means that I actually have to start with inverted X and Y. Because if I start with inverted X and Y, when I break the line and change the sign, the lines cancel out. And I will end up with X and Y. So what is really an AND gate, right? It is just this. This is the NAND gate, right? This is not AND, right? This is not AND, right? Not AND. So if I invert the things coming into the gate, I will get an OR. So this is your AND, right? This is an AND gate, and then you do the NOT, right? This is the same as AND gate, and we do the NOT. This is literally what I have over here, right? NOT AND, NOT AND, right here. Okay, so once you invert the actual inputs coming in, you get a perfectly good OR gate. So this looks like I'm replacing one gate with three, and that does look very convoluted. But you will see very, very soon that once we start re-implementing the circuits, especially circuits that have a lot of inverters, okay, those circuits tend to simplify when you use NAND gates and NORs. So once again, here's another recap, right? The AND gate is just NAND gate inverted back into the AND gate. OR gate is your application of De Morgan's, and the inverter you just tie two inputs together. All right. So now we're going to talk about NAND implementation. So how do we implement NAND circuits? Well, first, you actually build your AOI circuit. You build the ones that you know how to build, right? And or an inverter. And then you're going to go ahead and replace every and or an inverter with its NAND equivalent. The ones that I just showed you. You know, if you have an inverter, you tie two inputs together. If you have an OR, you invert the inputs into your NAND gate. And if you have an AND, you obviously put a second AND gate, NAND gate with two inputs tied together. Now, once you eliminate all double inversions, basically you're going to end up with a situation where you're going to have a bunch of back-to-back inverters, or more accurately NAND gates with two inputs tied together. Well, those things, they cancel out. So once they cancel out, you withdraw your final circuit, and you usually end up with something quite a bit simpler. So let's take a look at this slide over here. So I have one inverter, I have two AND gates, and I have an OR gate, right? This is a very simple circuit. This is very straightforward, right? This is definitely not the hardest circuit you have seen so far, right? That would be your project that you have just hopefully finished, right? Okay, so what are we going to replace? Well, this one is going to get replaced with one NAND gate. This one will be replaced with NAND gate and another NAND gate with two inputs tied together. And this one will be replaced with three NAND gates. So let's take a look how. All right, so this is an inverter. So we're going to use a NAND gate. We're going to tie two inputs together, and we're going to put it in instead. Instead of this one, we're going to put in an AND gate and another NAND gate that serves as an inverter, both in this case and in this case. And over here, we're going to put these three gates. It looks to me like we're increasing the number of gates, but you will see in the end that this is actually exactly the opposite. So this is what you're going to get at the end, right? So take a look. We can eliminate every single back-to-back inverter. We can eliminate this one because you have two inverters together, right? See, they're ANDs tied together, so they're inverters. You can eliminate them if they're right next to each other and they have their inputs tied together. We can eliminate these two. So in the end, we're going to end up with 1, 2, 3 NAND gates. All right, guys, so here's the thing. This looks like you have 4 gates, and in the circuit, the AOI circuit that we had, we also had 4 gates. So what's the point? Why are we doing this? Why are we not using the other one? Well, there are two things that we are talking about here, okay? One is the number of IC chips, and I'm going to talk about this a little later. And the other one is the number of transistors inside your logic gate. So you have read an article about transistors probably sometime in January. And transistors are the basic building blocks of your NAND and NOR and all of your logic gates. So for 74LS series, you generally speaking have about 6 transistors in one AND gate, and you have 4 transistors in your NAND gate. So 6 transistors in AND and 4 in NAND. So if you multiply these numbers, your AOI circuit will have more transistors than this one. The inverter usually has about 2, and NOR, I honestly don't remember how many. But the bottom line is you generally come out to a smaller number of transistors, and that brings down the price. Now, the logic gates that we actually use in this class, they're all more or less cost the same, because there is not just transistors in them. But if you are building something out of other types of components, this is going to be a consideration. So on this slide, I have a little proof of the equivalence. So if you really want to slog through all of this Boolean algebra and De Morgan's, feel free to do so. It's quite obvious that this is the case. All right, guys, so I have talked about transistors and how NAND gates have less transistors than ANDs. There is another thing you have to consider in this circuit, and that is the number of ICs. So if you look at your inverter, your AND gate, and your OR gate, your inverter comes in its own separate IC, right? It usually comes in a set of 6. Your AND usually comes in a set of 4, and your OR comes in a set of 4 as well. You have seen that when we were breadboarding majority vote, right? I kept referring back to the pinouts. Now, when you look over here, they're all NANDs. So they all come on the same IC chip. Now, NANDs also come in a set of 4. So this is just one IC chip, while this circuit over here is 3. Now, in this circuit, where we have 3 IC chips, we're not using 5 inverters, we're not using 2 ANDs, and we're not using 3 ORs. That's a colossal waste. In the circuit, when we're using the NANDs, we're using them all. So there is no IC chip, there is no gate on that IC chip that is not doing any work, which is great.